The story starts way back, not with silicon chips or cloud GPUs, but with the human brain. In the 1940s, researchers like Warren McCulloch and Walter Pitts were obsessed with this idea. Could we mimic the brain using logic and math? The McCulloch-Pitts network was a theoretical and mathematical model, not a physical machine. It was more of an abstract model of thought on paper, nothing fancy. They were not trying to build chatbots, they were trying to understand cognition itself. They boiled neurons down to simple binary switches, each receiving binary inputs, 0 or 1. Each neuron performed a logical operation, like and, or, not. If enough inputs were active, the neuron would fire. Otherwise, it stayed quiet. That was the first neural network. This network could be arranged to perform logical computations, but it did not have layers as in modern neural networks, nor did it feature learning or adaptation. Fast forward to 1958, and Frank Rosenblatt introduces the perceptron. It was inspired by biology, but implemented on a computer. It could take multiple inputs, apply weights, sum them, and then activate or not. The dream? Machines that could learn from experience. Rosenblatt even claimed it would eventually walk, talk, see, write, reproduce itself. Spoiler, it didn't, not then. The perceptron had a fatal flaw. It couldn't solve problems that weren't linearly separable, like XOR. And by the 1970s, AI fell into a winter. Funding dried up, hype turned to cynicism. Then the 1980s came, and with it, backpropagation. This was huge. David Rumelhart, Jeffrey Hinton, and others showed how you could train multi-layer networks by propagating errors backward. This let the system learn internal representations, not just memorized inputs, but abstractions. Now neural networks could solve XOR. They could start recognizing patterns in images, sounds, text. How? Imagine a team of chefs crafting a complex dish. Each layer in the neural net is a chef, adding their own ingredient. The final taste is the output. If it's off, we don't scrap the whole thing. We trace back through the kitchen, figure out who overdid the salt or underdelivered on spice. That's backpropagation. We taste the result, compute the loss, then go backwards, telling each chef exactly how to adjust their contribution. Not too much, not too little, just right. And over time, dish by dish, the network learns to cook. Still, the compute was limited, training was slow, real-world use was niche. Everything changed around 2012. Something dropped that smashed benchmarks in image recognition. ImageNet, trained using GPUs built by Hinton's team. Before it, most machine learning was hand-engineered. You'd spend months crafting features, writing code to extract edges, detect corners, tune filters. Less intelligence, more brute heuristics. Computer vision, especially, was a mess. Image recognition systems were fragile, clunky, barely worked at scale. The ideas were there: backpropagation, multi-layer perceptrons, even early convolutional nets. But nobody took them seriously. They didn't work on real problems: slow, unstable, underpowered. But Hinton and his students kept pushing. One of them, Alex Krzyzewski, took the parts everyone ignored: convolutions, ReLU activations, dropout, backprop, GPUs, and fused them into something big. That something was AlexNet, a deep convolutional neural net trained on ImageNet, a massive visual dataset with 14 million plus labeled images across 20K categories. AlexNet crushed the 2012 ImageNet Challenge. Top 5 error dropped from 26% to 15%, a leap like going from candlelight to electricity. This wasn't just a technical win, it was a cultural reset. It triggered the deep learning boom. Networks got deeper, datasets exploded, compute caught fire. Suddenly, deep learning wasn't just theory, it was state-of-the-art. Speech translation, image gen, drug discovery, all got the DL treatment. Companies poured billions into AI. Hinton joined Google, Sutskever would co-found OpenAI, and AlexNet became the symbolic birth of modern AI. ChatGPT, Gemini, DALL-E, Stable Diffusion, they all snowballed from here. So, what is a neural network? At its core, it's just this: a bunch of simple units, neurons, arranged in layers. Each neuron takes input, multiplies by a weight, sums it up, passes it through a nonlinear function. The final layer produces some output, classification, prediction, whatever. You feed it data, compare the output to what it should be, and nudge the weights to reduce the error. Do this millions of times, and it learns. Here's a dead simple Python version. That's basically a single neuron. Stack a bunch of these into layers, add nonlinearity, let them pass gradients, and you've got a modern neural net. But the real magic isn't in the math, it's in the emergent behavior. Large networks trained on vast data start doing weird human-like things. They write code, they understand sarcasm, they generate art, they reason in strange, blurry ways. So yeah, a neural network is just matrix math with a bit of nonlinearity, but it's also the closest thing we've ever built to synthetic thought. And we're still figuring out what that really means. We've built something remarkable, yes, but maybe the most intelligent question now isn't how far can we go, but why are we going at all?